Recording. Recording during this session. Okay, it says it's recording during the session. Unless there's something on Zoom that has changed. It says recording on mine. Does it on yours?
Yeah, I'm recording. I just click the recording.
Yeah, but you see the recording tab on
Yes.
the Zoom thing? Who asked us about not recording? Any?
I did.
It
When I
says-
said it was not recording, it is now recording.
Okay.
So I'm guessing that's on Jessica's end.
I have no
So we
idea.
can also be a co-host. We can both be a co-host. So you can, if you want to record on a computer.
All right. All right.
Okay, I just wanted to ask a question. So if we went in person always, it would basically become like a hybrid where you could choose to go in person.
Well, if you can't make it, you can watch it on Zoom. But if you can make it, I think it's more effective. That's my opinion, though. I've talked to a couple of professors that are doing it. And I remember one in particular is Dave Irwin, who wrote a book I'm referencing and using this problem. So I'm just telling you what I've found out from other professors. They prefer Zoom. And I don't have any idea what's going on with this camera of mine. It's plugged in. And as far as I know, everything should work. Give me one last chance on this because we have material to cover today. I've noticed one thing. Occasionally when you get updates, sometimes the updates cause legacy software not to work. Well, that didn't work. Let me share the screen. Wow. All right. There's 70 people here. Let me see if I can share the screen and just show you the results. So far, this is what we got. Hold on. Can you see the screen, class? Or not? You can? So what I've got is 32 or 46% want in person, 54% don't. There's 70, there's actually 90 some students in here, so we'll wait a while. But that's what I have so far. All right. More people show up, so be it. Now, you should be able to see this question in chat. I apologize for this thing. It would.
We're just looking at your desktop right now.
Yeah, I'll tell you what the problem is right here. If you can take a look at this camera, and it was working earlier. And I'm not doing a thing, by the way. And that should come up. So now I'm going to do one thing here. I've troubleshot this thing. This is this doesn't work. We're going to have to, I'm going to have a makeshift camera right there. Well, anybody's got any suggestions? I'm all ears.
Try reinstalling the software.
Yeah, I'm a little concerned about the time. I could do that. You know, but let me just try one last thing. Hey, wait a second. Maybe that's it. That might have been it. I'll be. Malware bites this time. Can you all see this, class? I apologize for the time this took. Y'all with me, everyone? Y'all still there?
Yes.
Yeah.
Hold on for 1 second. Let me get this thing out of here. All right. There, you should be able to see me too, right? All right. I never had problems with malware bites before, but in this day and age, anything's possible, and it does happen. So before I do anything with power, and I will somehow make this up this day, do you have any questions about the previous homework? Any at all?
Can you do 3.45?
Yes, absolutely. 3.45.
Yes.
I want to say one other thing about inductors. Like capacitors, there's only a couple of simple rules. If you follow them, you won't have any problems. 3.45 is this one. And my book's a little messy, but what it comes down to is this. Can everybody see this okay? Class? Jessica,
Yeah.
I think you're the only
Yes,
person
yes.
I hear and see. Let me try one thing, guys. Okay, I got myself and Joseph with screens, and that's it. If you've got a screen on, I can't see you for whatever reason. So right now, with this one, this switch is closed to T equals 0. Do you all see that? Right here?
Yeah.
All right, now an inductor, remember what I told you, it looks like a short circuit if nothing's changing with time. Do y'all hear me? A short circuit, a piece of wire. So for T less than 0, Jessica, you asked this, right? So for T less than 0, if you take one look at this, this is a direct short, right? Class? Y'all see, I mean, give me
Yeah.
some indication of life out there, a thumb up from somebody else besides Joseph and Jessica. Are y'all there? Okay, Amanda, thank you, thank you. If you can just show me there's somebody besides 2 or 3 people, because it helps. All right, now I mean, you voted, there's obviously people there. If that is a short circuit, I want you to listen before I just redraw. If that's a short circuit, does this 6 ohm resistor have any bearing at all on the behavior for T less than 0, class?
No.
No.
And you're right. And the reason it doesn't is because it's shorted. All the current will go through here. It's like that 6 ohm right here is not even a factor. Do y'all see that? Some indication, just nod, do something, right? You don't have to give me thumbs up every time. Now, if that's the case, look, if that's the case, all the current that flows through that 4 ohm or flows through that 2 ohm is flowing through that inductor. Do you all see that? Take a good look and make sure you do. It's important. All the current that flows through the 4 ohm is going to flow there, and all the current through the 2 ohm. In fact, what we could say is this point right here is just like ground, isn't it? Electrical potential is the same. It's 0 if you wanted to put a ground here. Right? Do you agree with me, class? All right, now how much current flows there for T less than 0? I'll write this down, but just think. Well, 4 over 4 would be 1 amp flowing here, right? 4 volts over 4 ohms is 1 amp this way. What about over here? All right, that 6 ohms has no bearing. I just made that point, correct, class? So the current flowing here from this 6 volt would be 6 over 2 or 3 amps, right? How many see that? Some indication,
Yeah.
right? With me? So if you've got 3 amps caused by this 6 volt and 1 amp by the 4 volt source, the total would be, I mean, you're going to have 3, right? Plus 1 or 4 amps, right? Agree?
Yes.
Now you asked that about this, Jessica, and I'm trying to do this. So,
Wait, I'm confused why you add them.
all right, I want you to take a look at this. This is effectively a short circuit, right?
Right.
Who's asking this?
Amanda.
All right, Amanda, if that's a short circuit, that 6 ohm doesn't matter, right?
Right.
Now, I could go ahead and do a source transform. I could say this is equivalent to a current that's 4 by 4 or 1 amp with 4 ohm in parallel, right?
Oh wait, are you adding them because they're both going into the node?
Yeah, and there's only one way out. It's this way.
I got it now.
Okay.
Is this for T less than 0?
Yes. Yeah, I'm starting always at T less than 0. It's the way I do it. So for T less than 0, all right, I'm going to say IL right there for T less than 0 is equal to, in this case, it's going to be what? 3 plus 1 or 4 amps. Do you all agree with that? And I'm calling the positive current flowing down. If I need to draw this, I will. Maybe I should. But I think it's pretty evident, this part, right?
Can you repeat again? You said for T less than 0, it's still closed, right? So if
Yes.
it's closed, then it becomes a wire, is just short?
Yes, as a matter of fact, I'll redraw that circuit for you since there's some uncertainty. Please be careful and watch this. Now, if you haven't done this stuff, this is going to eat you very quickly because we are going to do some power today. If you've got to stay up with this. So if you have 6 volts here, right there, and then you have 2 ohms in series with it, right?
Mm-hmm.
Now, normally you would have 6 ohms here, right? But that 6 ohms isn't going to change. This will be for t less than 0. That's not going to have any effect because that inductor looks like a short circuit, doesn't it? And I'm calling this current positive. So this would be IL t less than 0. On this side, we have 4 ohms, right? And then we have 4 volts. Do you agree with that, everyone?
Yes.
Now, this is for t less than 0. You can look at this any way you want, and it's a standard kind of question to see if you know what you're doing. How much current is flowing down there? Well, this 6 ohm has no bearing because it's in parallel with that short circuit. No current will flow through that, all right?
Yes.
All the current flows through that. How much current? Well, effectively, this point is like ground, right? I can just find the current flowing here and then add it to the current flowing here, right? It has to go down that inductor, doesn't it, class?
Yeah.
Yeah.
All right, this current would be 6 by 2 or 3 amps. This current would be 4 by 4 or 1 amp. Therefore, all the current through here, this way would be 4 amps. That's the only thing I'm saying for t less than 0. Agreed? How many see this? With me? John, do you see this or not? John Wells, I mean, if there's hard to see or whatever, let me know. You all see it? I'm getting a bunch of, all right, good. I want to just move on. If that's the case, I've got the part for t less than 0. Now let's go for t greater than 0. For t greater than 0, I come over here, right? And what do I see? Well, that switch is open, right? Now, if that switch is open, isn't that taken out because it's only connected at one point, which doesn't count? So this whole part on this side goes away, doesn't it, class? Now look at this. We're going to go and take a look at just this part of the circuit. I'm going to redraw. Here I've got an inductor like so. And then I have a resistor of 4 ohms. And I have a voltage source of plus to minus 4 volts, right? As such. And this is L, which is 2 henries. And what I want to know is the current through that inductor as t goes to infinity. Well, what do I replace the inductor with at t equal infinity, anyone? Same thing for t less than 0. What is it? Nothing's changing with time as t goes to infinity for a DC voltage source, is it, class? Everything's stable. So what do we replace it with?
So it's just a short.
A short circuit, a wire, however you want to put it, right? If that's a short circuit, how much current flows through that?
Everything.
Everything.
Would it be 1 amp?
Well, sure, 4 volts over 4 ohms, 1 amp. It really is that easy. If you think it's too easy, you're right. It is that easy. So this means IL for t less than, or I'm sorry, t going to infinity right here is equal to 1 amp. Now I have the current, it's t equals infinity, the current for t less than 0, right? Where the switch transitions. Now I need to calculate R Thevenin. This one's kind of obvious, right? This is the circuit for t less than 0. R Thevenin occurs for t greater than 0, pardon me. R Thevenin is the resistance seen across the terminals where the inductor would be if it's taken out. And it's got to be a Thevenin equivalent. So this voltage source is a short, right? You all see it's just 4 ohms, right? Any kind of, any heading on anything. So 4 ohms. Now somebody besides Jessica, what is tau then? Anyone?
1/2.
Yeah, tau would be equal to L over R Thevenin, right? And L over R Thevenin is going to be 2 over 4 or 1/2. And the unit for tau is seconds. I usually don't stress that. It's almost implied because it's dividing into t, right? So now you have your general equation for current. I'm going to write it. IL of t, this is through the inductor, is equal to K1 e to the minus t over tau plus K2. I will encourage you to write this equation down, even though some of you see through it and know what K1 is. Just write it down and keep doing that until it becomes second nature. Now, I know that K2 is the current as t equal infinity. Do you all agree with that? Because at t equal infinity, e to the minus infinity, I mean, this thing goes to 0, so I know it's just K2. I can therefore write IL of t is equal to K1 e to the minus t over tau, and I can put 1/2 if I want, it's not essential, plus the current at t equal infinity, which is 1 amp, right? And how do I get K1 last thing?
You substitute, you put the t, when t goes to 0, t equals 0, you substitute the value.
Right, and these are really the initial and final conditions. So the initial condition was current at t less than 0 is the current at t greater than 0. That current itself was 4 amps, right? So I say 4 here at t equals 0 is K1, e to the minus 0 is just 1, plus 1, or, yeah. Or here that K1 is equal to simply 3 amps. Agree? Y'all with me, class?
Yeah.
Honestly, this is something, if you do these things, you're going to see it. Just remember one cardinal rule that you didn't on the last quiz. Replace the element with its equivalent for t less than 0 and t goes to infinity. The element here is an inductor. It is replaced with a short, and you're only looking through the current through it. With a capacitor, you replace it with an open circuit. And if it's an open circuit, no current can flow through that. So if there's a resistor in series with it, the voltage drop on that resistor is 0. You got me on that? That was on the last quiz, and a lot of people apparently got that wrong because of that fact. Okay, class? All right. Now, I've got that, and the question that they wanted was the current there, so that's the answer, right? Now, I'm going to ask you a question since you asked me a question. If I wanted the voltage across here, that right here, that voltage across the 4 ohm, I'm just showing you this is the voltage across the 4 ohm. How would you get it anyway?
Would you just multiply the current that you find times the resistor?
Yes, I could say that voltage across the 4 ohm as a function of t would be the current, right? Which is going to be this equation, which is going to be what? 3 e to the minus t over tau plus 1 times the resistance 4. Do you all agree with that? Now, if I ask the power, instantaneous power, we haven't touched power in a while, it would be either the current times the voltage, right? Or the voltage squared divided by R, or R times the current squared. Do you all hear me on that one? Any of those forms would be acceptable for the instantaneous power. Now, is there any other question before I move on with the inductor problem? Specific questions. I gave you several. I provided the solutions, and I went through the most difficult one, which was 344 in the last lecture. Now, level with me, guys. How many actually took a shot at some of these and worked them? You can just level with me. Did anybody that took a shot at them have any major problems or concerns or questions?
I was kind of confused on 3.43.
Okay. Jake? All right. Can you see this okay? Everybody?
Yes.
Let me talk through this. And I encourage you to get to a point where as you're looking at these problems, before you just writing them down, start working them. Take a look and ponder this. If I take a look at this for t less than 0, you know this inductor is a short circuit, right? Now just listen to me on this. Do you agree with that? So if that's a short circuit, I look at this and what do I have? Well, I've got a couple of resistors here. That's 8 and 4. They could be combined as 12. Do you agree with that? They have no real bearing, so make that 12. Right? Then over here, I've got 3 ohms, and that's where I want the current through the 3 ohm, and it's in parallel with 12, isn't it? Do y'all see this, class? Now just listen to me. I'm after the current through the inductor for t less than 0. Now, what I could do is this, and there's several things I can do. I say, well, if I have this current, I'm going to take, and what I'm going to do is figure out the amount of current that's actually, you can do it a lot of different ways, by the way. this is the way I would do it if I was you. I would probably say that this one I'll actually redraw. But here's what I'm after. If I take a look at this, I know I got a current source and I got a switch. And my real problem is T less than 0. So what I can do, that's 12 ohms. Then I take a look at this. I have 6 and 6. That's 12 in parallel with 3, right? Well, I mean, do you agree these two are in series, class? Right? So if you've got 6 and 6 is 12 in parallel with 3 is what? Well, it's 3 times 12 is 36. That's an odd number. I'm surprised he did that to you. So you're going to have you got 36 over 15. That's just one of those numbers I hate working with. I like nice round number. So you're going to have basically 36 over 15 ohms here, whatever that is. And what you're going to do then is have that in parallel with 12. Now, you know that this current, 120 milliamps, is going to do current division. The amount of current that goes through this network would simply be 12 over 12 plus 36/15. So I'm not going to work this right now in my head. And then once I got that current, I'd have to do current division again. That's one way. Are you with me? That's one way. And if you're quick on this, I mean, chess players get this stuff real quick. If you can do it that way. If not, what I'd suggest you probably can do, try to get this glare. What I can do is this. Do you all agree if I have 12 in parallel with 120 milliamps, right? I can get that as a voltage in series with 12 ohms. Do you agree with that? This is going to be source transform. So I can take that and I can make it 12 ohms, right? And then I really have 0.12 times 12, right? Or I've got what? That's going to be 144. What is that? 1.44 volts, right? 144. This is 1.44 volts, and I got that by taking 120 milliamps times 12 ohms. Do you agree with that, class? All right, because they're in parallel, right? In the source transform, current in parallel with the resistor is a voltage, which is I times that R with a series resistance of 12 ohms. Now I come over here, that switch is a short, and I have 3 ohms, and then I have 12 ohms, right? Like so. And really, I want this current. Do you agree with that? This is all for T less than 0. Now, if I want this current,
You're super out of focus.
is this okay? You okay now? All right, now look. Are you with me so far?
Yeah.
And I should have done this in the first thing. I can see that this 12, I can do a source transform, just go back to the original circuit and I'll redraw. I have 12 ohms. I'm going to do a source transform back to the original. This is a current source of 120 milliamps. The switch is closed. I'm after this. The 3 ohms, I'm after the current here. That goes there, and then I have a total of 12 ohms here. Now here's what I'm going to do on this one. I just redrew the original. I'm going to say this 12 and this 12 are in parallel. Do you give me that? Take a look, everybody. That is in parallel with that. I should have done this in the beginning. So that means it's equivalent to 6, isn't it?
Yeah.
If it's equivalent to 6, I'm going to get rid of that one and just make this 6. Now, take a look. I have 6 in parallel with 3, don't I? I've combined those two 12 ohms. If I have, and I want the current through that 3 ohm, I can say this current would be equal to the total current which would be 120 milliamps, times the opposite resistance, 6, over the opposite plus the adjacent, or 9. Do you agree with me, class? Standard current division, and if you do it that way, that's going to be 2/3 times 120 milliamp, right? So 120 by 3 is 40 milliamps, times 2 is 80 milliamps. Now that would be the current IL for t less than 0. I'm trying to not go too fast, but trying to make the best use of the time, right? This is for t less than 0. Let's take a look at this circuit again. Now, once, JT, you asked about this, right?
Yes.
So once this switch opens, do you see that this source is completely out of the circuit, class? If that's completely out of the circuit, what must the current be as t goes to infinity? Anyone?
0.
0, right? No source, no problem. It goes to 0, right? Because it dissipates all the energy. Follow me? There's not any source that sustains that energy. Now, the next thing you need is R Thevenin. I'm trying to just work from this to save time. If you look at this class and you wanted R Thevenin, you have to snip that right here and here, correct?
Yeah.
Take it out and look and find out the equivalent resistance. What is it?
6.
Plus? How many see all these are in series? 6, 6, and 3. Do you see that? Can you see that or not?
So it would be 15.
Right, but I mean, do you see the reason for it? When you pull this inductor out, if you measured with an ohm meter right there, you would see 3 plus 6 plus 6, right? Or 15 ohms, correct, class? How many see this? I see some puzzled looks, and it's puzzling me.
Yeah.
What you
Yes.
might say.
Yeah.
They're all in series, aren't they? Amanda, do you see this? All right. Okay, now if you don't, let me know, because I need to know what you don't see, because it seems very apparent to me. If I just take that out, the only way current can flow is through all those in series, right?
Okay.
And if somebody can take a look in the chat, what's going on, let me know. I'm trying to do this. So now I have that, and I've got R Thevenin for this problem. R Thevenin was 15 ohms. Somebody want to tell me what tau is? It's what? L over R Thevenin, correct?
Yes.
All right, and L is 0.6, and R Thevenin is 15. This is one of those ones I wish I didn't have to do, but I'm doing. Y'all agree with that? Can y'all calculate tau? Now, we go ahead and we have to still solve for K1, don't we? Or do we? In a sense, we don't. Why? That tells me that K1 is the current at t equals 0, doesn't it? When the current at t equals infinity is 0. Isn't that right, class?
Mm.
All right, now that means I have the equation. I have IL of t for that is equal to 80 milliamps. Don't forget the units, e to the minus t over tau. You got tau here. I don't care about it. Now,
It's
please,
0.04.
0.04?
Yes, sir.
Okay, that's fine. But my real thing is getting back to here. I want you to just pay attention to one thing that's important. Now look, that current is flowing this way, the direction of that blue arrow. Take a good look. We know what that current is, right? Now listen, if that current's flowing this way, you see how there would be a voltage plus to minus that would be equal to that current times 6 ohms in plus to minus. How many see that? It's very important. You see that it's the polarity of that, right? I times R, I is known now. R is 6 ohms. This would be the plus to minus voltage, correct? Y'all with me? All right, but that's not what's wanted. They want this voltage, so now we throw a minus sign in front of it. How many see that? This is a great problem because this has all the mistakes that can be made. All right, polarity mistakes, mistakes with this business somehow being in the circuit after t greater than 0. I promise you that what I'm showing you is important and it's often missed. Right here, the polarity is important. Are we good with that?
Wait, can you explain why the current's going down to the inductor?
Remember,
two
I
currents are
chose the direction of the current, right? Initially, you got to pick a direction. So if I want the current in this direction, I find it in that direction at t less than 0 when that's a short. You follow me, Evans?
Yeah.
All right. Now, when that's a short, I've said down. We got from what we did was we combined the 12 and the 12 here to 6, and then we did current division because we have 120 milliamps going into the node right from here to here, right? And once we had current division, we saw that was 80 milliamps going down to that 3 ohm, if you look back.
What's up? What's for the current division? How did you get that it was 6/9 times 120 milliamps?
Okay, for current division, who asked this, by the way?
That was me.
All right, current division always says what? You take the resistor you don't want the current through, right? If they're in parallel, two resistors in parallel, then you add together the resistor you want the current through plus the one you don't want the current through, and you're going to get a fraction, something less than 1. You multiply that by the total current going into the node. How many remember that current division? Okay, I mean, you should. Current division is like voltage division, only now the resistor that's the smallest has the most current, right? With voltage division, the resistor that's the largest has the most voltage. Good?
Could you just do the current division in 341? Like I get the rest, but for some reason I'm messing up on that first part.
Yeah, but before we move there, let me take care of this problem. 341's is up here. All right. Just let me take care of this problem in its entirety, hopefully. All right, Evans, you asked about this. I've selected the current going down. I didn't have to choose it down. I could have said it's going up, but then I had a negative value from our initial current.
I see. You chose the current direction when you were doing all those source transformations.
Well, I arbitrarily chose it downward.
Arbitrarily
Which means, yeah, when I calculate the value current, it means once this is broken off, it's circulating in the counterclockwise direction.
I see.
Yeah. That means this is plus to minus. The voltage would be developed such that I times this R, which means this voltage would be minus that. That's my point. All right. Now,
So the voltage is plus to minus because the current is going down?
well, you can think of these as, have you worked with a voltmeter, Brooke?
It's been a while.
A voltmeter has a plus and a minus lead to it. If you've ever done this with batteries, any guys that mess with cars, you know this. And you go ahead and you put the plus on one side, the minus on the other. Now, if you do that to a 12-volt car battery and you have them reversed, you read a minus 12. All right. It's always with respect to two things. If you call this the minus and this the plus, and you measure voltage. If it's minus, it means if you turn the leads around, you get a plus. That's all it means. All right. That's all it means. Now, back to this thing. Because the current's circulating this way, and we know that the voltage is developed such that positive current means current flowing into the positive terminal, right? The voltage here would be plus to minus I times that resistance, plus to minus here. But the actual measurement is here. Think of a voltmeter. So if I put the plus lead here and the negative lead here, I read a negative value. How many see that? All right, I'm not trying to, go get a voltmeter and a battery. I think it'll be clear to you if you mess with it for a little bit. Now, back to this problem that Brantley, you asked this, right? All right, when we look at this, first for t less than 0, that switch is open, right? Now just listen carefully. I think we can do this without much of a problem. That's a short circuit for t less than 0, isn't it? I want to make sure everybody sees this. For t less than 0, that inductor is a short, correct? Now this is the way I'm going to reason through it. So really I have 3 in parallel with 6, don't I? And 3 in parallel with 6 is 2. 3 times 6 is 18. 3 plus 6 is 9. 18 by 9 is 2 ohms. That's in series with 2 ohms, right? I didn't even need that though. I went and did that for no reason. We've got 2 amps going through here, don't we? This isn't a voltage source, it's a current source. It says it's 2 amps. Do you follow me? Doesn't it say I mean, 12 amps.
Well, thanks.
12 amps. Okay, 12 amps, right? So if there's 12 amps here, I've got the current. I don't need to do what I was about to do. If it was a voltage source, I'd need to do that, but it isn't. It's a current source. So you asked, how do I get the current division? Well, if this is a short, now you asked about, if I want this current, and I'm just going to put it right here, I want that, and I'll call it I2 for t less than 0. I would say I2 is just the total current, which is 12, right? I'd be attentive here because you asked. Then you do the opposite resistance. I want the current this way. The opposite is 3, isn't it? And then you sum the two that are in parallel, which would be 9. Got it? And that means
Yes, thank you.
the current would be what? Be 1/3 of 12 or 4 amps. Agreed? All right. And that's it. By the way, what happens to the current as t goes to infinity when that switch shuts? The current over here. Class? Anyone?
It becomes a short. So
Well, when this becomes a short circuit, what does this do to that 12 amp source? Anyone?
this means it can just go in a.
Eliminates it, right? It's a short circuit, right? There's no voltage difference between here and here. There can be no effect of that part of the circuit. It basically isolates that part. Y'all see that? So if that's the case, what's this current going to go to as t goes to infinity through the inductor?
0.
It's got to go to 0. All right? Don't be afraid to say it. It's as obvious as it seems. All right. All right, guys, with me? All right. Now, where I was about to go is power. I'm going there. It's going to be, we lost some time in the beginning due to malware bytes. Does anybody else use this besides me?
Malware bytes?
Yeah.
Yeah,
No?
that's great.
Well, it wasn't today.
But like it's really slow as far as antivirus software goes, so I prefer to use a different one.
This is my take on a lot of this software. It works great when it works great, but when it doesn't work, it really messes up everything. And especially if you have legacy software. This is an old document camera. All right, I'm just going to make that statement and leave it alone. Now, when we talk about power, this is the essence of what I wanted to get at. Because people will, if you look in the book, oh boy, without bad-mouthing it too bad, there's a lot of assumptions. Some of the assumptions are that you're very good at everything you've been taught. I know better. I don't make that assumption. I make the assumption you're not very good and you need reminding. So I'm going to teach it the way I teach it always. I don't assume too much other than you know what a resistor is and you know what an inductor is and a capacitor. So with that in mind, listen carefully. And if you have to go in a minute or two, so be it. I'll pick it up where I left off. And I understand some of you do have to go. And believe me, I wish I could stretch time, but I can't. So I do understand that. And somebody's going to say, well, what's the quiz on Friday? Well, the quiz is going to be on Monday because we can't do it Friday because we didn't even cover the new material. So it will be on Monday. Got it? Oh, you want the results of the survey. Yeah. Thank you. Or the poll. Hold on. Where is that poll?
So if we go over power on Friday, could that
Wait,
be on the
one
quiz
sec.
on Monday? Or
It
oh,
sure
sorry.
could. It sure could. But it will not be a difficult. Y'all see the results? Class? Oh, you can't? Isn't that sharing?
No,
We're still on your dot cam.
Well, oh, goodness. All right, hold on. Now can you? Can you see the results of the survey now?
We're seeing your desktop with OneNote on it.
There's, all right, this is very bizarre. OneNote's
Just
on.
print screen it and then show us the print screen.
I'll snip it. I think I can do that. Give me 1 sec. I'll just tell you, I want in-person lectures always 44%. I want quiz lecture on Friday, only 56%. And as a matter of fact, let me just see if I can do anything. Now see if it's there. You see it now? Hopefully you see it now. Yes? Yes?
Yes.
Okay. That's as fair as I can be. I know we didn't get most of the class. We're missing some people, but I can't do any better than that, all right? I'm sorry. This has been one of them days. All right, back to power. More questions? No.
Quick question on the one we were just doing, 343. To find that V naught, would you just divide that current by 6 ohms and make a negative?
This 343, the only thing you would do is take the current and multiply it by 6, wouldn't you? You don't divide.
Oh, multiply. Yeah, multiply.
And that would be the voltage, but you'd have to throw a negative sign in front, right?
Yes. Thank you.
That's it. Okay. My apologies. Stuff works just before and not during, but that's okay. Now, if you have to go, you have to go. If you don't mind, I'd like to talk a little bit about where we're going, and I'm trying to set the stage for how simple this is, not how difficult it is. And in the book, I believe it's chapter 4 in your book of 5, and it talks about power, and he talks about polyphase circuits, means more than one phase. Don't worry about it. All right, let me show you as best I can. So when we talk about any type of power, you always start with the definition, which is instantaneous power. And I'm going to get my doc cam back up. So that's instantaneous power. P of t is equal to I of t times V of t. What it says, if you have any element,
Professor, your pose is in the middle of the screen and blocking everything you write on paper.
The what?
Your pose is still in the middle of the screen.
Thank you. Strange, I can't see it, but you can. All right.
You can just click OK and it'll go away.
What's that?
You can just click OK on the poll and it'll go away.
Yeah, if I
The poll is on our end. Like,
yeah, I can't see the poll. I think you have to click the poll.
Yeah, you just click close and it goes away, man.
Man, not referring to Dr. Baginski.
Yeah, not you, Dr. Baginski. Yeah.
I know. But you got to understand, new technology like this is always interesting. It's interesting because I hear sometimes just bits and pieces of conversations when there's more than one person. And all right, I hope everybody can close that poll and see this. Do y'all see it? Now just listen. That's all you have to do. If I have a voltage here, V of t, it doesn't matter if it's time varying or not. And I have something here, an element, it doesn't matter what it is. It can be a resistor. I'm just going to use R bar, could be anything. Then the instantaneous power through there is the current I of t times the voltage. That's instantaneous. That's what you'll see in his book. That doesn't do much for you. An empty box that was like, what's in there? Think of it as a resistor for starters. And let me go ahead and expand. So that's instantaneous power. There's also something called average power. And the average power is just equal to the integral of the instantaneous power dt over a period and divide by 1 over t. Now you've had averaging since probably 8th grade or maybe 5th grade. When you average anything, you sum or integrate the values over a certain length of time, space, whatever, and then you divide by the time, space, or whatever, right? That's an average. It's as clear as it can get. Now, when you do an average of power, if it's a DC source, I want you to hear me now. How many people do I have here watching?
33.
Well, I'm glad you're here because I'm going to tell you something right now. This is one topic that students get lost in when it's taught with the assumption that everybody understands everything that was taught. I never make that assumption. I know so much better. A good chunk of you have things missing. But if that's V of t and I have a resistance R, Now, do you all agree nothing changes with time? That voltage is a V naught from the beginning of time to the end of time. And that resistance is R. There is nothing that stipulates things are time varying. Do you agree with that?
Yeah.
If I find the current here, that current I of t would just be a constant, and that would just be V naught over R. There is no variation with time. Agree? Now, it also means that the power that would be dissipated by that resistor would be a constant, and it would be
Out of
equal to,
focus.
thank you. That power would either be I of t times V of t, or it would be V of t squared over R, or it would be I of t squared times R. All of those are correct. Regardless, I'm just going to put it here, P of t would be equal to just V naught squared over R. Now you can see that's true because the voltage does not change versus time. Do you all see this, class? The voltage does not change versus time. That means the instantaneous power here would be equal to the average power. You can average that over any length of time. It's still going to be just the value at the instantaneous value. Do you all see that, class? Sometimes I make these points and people look at me like, why are you even saying that? Of course we see. Well, I know some people don't. It doesn't ring true. I'm making sure there's no variation in the power. Therefore, the average is the instantaneous. Now, here's where things change. Pay attention. And this will do you a service and a half if you just listen to me. If I put a voltage source here that is not constant, and I'm going to make this just some V naught cosine of omega naught t. Now that's a time varying voltage, right? I'm going to put the resistor here. And if I take a look at this, I got a voltage, I would have a time varying current, which would be V naught divided by R times cosine of omega naught t. Does everybody agree with that? Right? Now, when I take a look at the instantaneous power that's being dissipated by that resistor, that would be V of t times I of t, or it would be, just watch, I'm going to take this times that, I would be V naught squared over R, and it would be a cosine squared of omega naught t. Now, do you all agree with that? I took the voltage and multiplied by the current. The key thing is I get a cosine squared, right? There's a cosine there, there's a cosine there. You multiply them together, you get cosine squared. Do you agree with that? You could have just as easily said V squared over R and gotten this, right? Are you with me? Now, this has a period, right? If you think about it, cosine squared can be broken up as what? 1/2 plus cosine of 2 times the argument omega naught t divided by 2, right? But it would be periodic. Do you all agree a cosine or a cosine squared would be periodic? It repeats itself. Agree?
Yeah.
Yes.
And that means there's an average power that needs to be calculated that will be different from the instantaneous. Now, if you look at this just for a second, you all agree that that's the instantaneous power, correct? Now listen carefully. The peak value of the instantaneous power would be when the cosine is 1. Cosine of 1 is really of 0, of omega t equals 0, of omega t equals what? Pi, well, really, that'd be -1, 2 pi, and so forth. But the peak value of this would be V squared over R. The minimum value would be 0, because when omega t is equal to pi over 2, it's a cosine of 90 degrees. That's 0, right? 0 squared is still 0. So the power would literally go from 0 to a peak, back to 0, back to 0. And here's what the power would look like. And guys, I know I'm talking a bit fast, but I'm just trying to get to the essence of this. So if you were looking at the power, the instantaneous power versus time, you would see this, wouldn't you? Well, actually, you would see from there would be 0. It started there. And basically, it would go from a peak to a min, peak, min, peak, min. Do you all agree with that? How many see that? It's going to bounce between 0 and a value of V naught squared over R, right? Now listen carefully. Do you all see that there would be an average value somewhere in there, right? It's going to be an average value greater than 0, less than V naught squared over R, right? Now,
Yes.
I'm going to end it showing you what that is. And most of you have had something like this. So let me just do it. If I was going to calculate the average value of that power, P av, right here, I would say it would be equal to 1 over the period, and I'll get to that in a second, times the integral, because this is periodic, the integral of V naught squared over R times cosine squared of omega t, right? dt from 0 to t. Capital T is used for the symbol for period in almost every engineering course or curriculum. Are you all familiar with the term period? It's the distance in time over which something repeats itself. In mechanical, aerospace, industrial, y'all understand that, right? It's universally accepted. Even physics, math, everybody uses capital T for a period. So if that's the period, you could calculate the period, right? You could say, well, the period would be where it repeats itself. If t equals 0, this argument's 0. Then if this argument is 2 pi, or if omega times the period is 2 pi, that would be the period. Therefore, t is 2 pi over omega naught, right? So you could calculate the period, and you could put it here, and you could put it here as well. Don't worry about this integration. I'm going to just show you how it simplifies in a heartbeat. Now, do you all agree with this? Here's where I end. You all agree that if you have cosine squared of just theta, that's really 1/2 plus 1/2 cosine of 2 theta? Simple trig?
Yes.
If you don't believe me, don't worry about it, but it is, right? Now, if I do that expansion for this, I just want you to listen to me. You can see I'm going to have a 1/2. It's like a DC value. It doesn't vary with time, right? And then I'm going to have something that's going to vary. Now that theta is really omega naught t. So this average power right here is 1 over the period. Just leave it as 1 over t. Then it's going to be the integral from 0 to t, V naught squared over R. And it's going to be 1/2 plus, then it's going to be 1/2 cosine of 2 omega naught t dt. Now, the only thing I've done is expand the cosine. This is the essence of what I'm getting at. Listen to me and we'll be done. That's a cosine waveform, right? Regardless if it's 2 omega naught t or omega naught t, anytime you have a cosine waveform, it does something like that, right? Now listen, isn't the area above a cosine waveform the area below when you do an integration? So if you would integrate a cosine waveform over a period from here to here, you see that the integral of a cosine waveform over any period would be 0. How many see that? Because it would be the area below. The negative area would be same as the positive area. They would cancel. How many see this and know this? Good? Amanda, you okay with that? John? I got to make sure, I don't know if it's too obvious, forgive me. So this will go to 0. Now this one is a constant, right? I have 1/2 V naught squared over R, integrated from 0 to t over 1 over t. Do you all realize that when I have a constant integrated dt, I just get t times that constant? When you put in the limits from 0 to capital T, you just get capital T times that constant divided by t is simply P av. This is the bottom line is just going to be equal to V naught squared over R divided by 2. Now that is the average power a resistor would absorb from a source that is cosinusoidally varying. I'll spend a lot more time on Friday developing this and showing you. Remember, the quiz will be on Monday, all right, not Friday, and I'll have to make plans because we didn't even get to this. Okay, class?
Are inductors going to be on the quiz as well, or is the quiz just going to be on power?
It could be on both. Who asked this? I mean, what I'm trying to do is get you to the point where you're ready for an inductor problem that's, I'd say, very obvious, and I mean, and a simple power problem, okay? In other words, you're always responsible all past material, but specifically, I'm trying to be honest with you. Don't think you're off the hook with inductors or else you won't do the homework. So I want to make sure you do. That's my bottom line.
So are we going to have 2 quizzes next week?
Possibly. Okay. You okay with that?
Yes, but
That's a really, no. Well, you're not having 3 if you want to think positive. From me. Okay. Just stay up with this stuff. I know we got a home game coming in, not this weekend, but next. We got Georgia this weekend. What is it, Arkansas following? I'm not sure. Okay, if you're going up to Georgia, be safe. Don't be stupid. Okay, now, since this is an office hour, any questions you have, and again, I apologize for the functional problem with the equipment.
Isn't the governor of Georgia suing the mayor of Atlanta for requiring masks?
I don't know. Really, I don't care. I mean, are you going to the game or something? Is anybody going?
God, no.
I mean, are you going? Anybody going? I don't really. No? I can't hear you, Gabby. Or did you?
I don't think anyone got student tickets for it, so I don't think anyone can like go to the game. But
No, there's scalpers always. Don't worry about it. If you're willing to pay, they'll find a way to get you in. But I'm not somebody that's going to drive up to watch us play Georgia early. Maybe the SEC championship game, yeah, but not this early in the season, especially with COVID. I mean, after LSU got the tar beat out of them, I figure this season's more or less a wash anyway. Amanda, you got more questions? No?
Actually, I did have one. Hold up, let me find it. So I was doing 3.36 earlier, and this may just be like, because I haven't done a ton of these yet, but it was finding like the solution found current when t was less than 0 first, and then use that to find the current through the inductor.
Yeah, and I'll tell you the problem. I'm just level with you. They're going to get an equation for current through this 8 ohms. Don't do that. I want you to just hear me. The answer is correct. I want you to know that, but the method is wrong. Always find the current through the inductor. Now, the reason I'm saying that,
Well, that's what I was doing.
Good, then you're doing the right thing.
Well, but when I did it, I found what they like. Okay, so I found 6 milliamps first for t was less than 0, and when I checked it, they did that first and then went a second step to find the current through the inductor, which I thought the 6 amp was that.
Just hold on for 1 second.
Yeah.
I want to just go through this with you, and I'm going to talk my way. Now, remember, anything they want, you get from the current through that inductor. All right? That's it. Now, for t less than 0, just listen to me. For t less than 0, we want the current through the 2 Henry. I want this current. Follow me? And I'm picking the direction going down. In my way of thinking, given an option, always go from top to bottom, from left to right. That's the way I always do it. And I try to be consistent. If I take a look at this, for t less than 0, that's a short circuit, right? I have equivalent of 12 in parallel with 6, correct? Right? 12 in parallel with 6 is going to be 4 ohms, isn't it? 4 ohms in series with 2 is 6 ohms, correct? Just think about this whole thing here is 4 ohms, isn't it? I mean, from here to here. Agree? Amanda?
Yes.
All right, 4 ohms plus 2 is 6, right?
Right.
That means the current here would be 36 by 6 or 6 amps for t less than 0, right?
Right.
If you got 6 amps for t less than 0, now you do current division. I want the current here. I'll call it I2. I2 here would be that current 6, right? And then it would be the opposite resistance, which is 12, right? Over 12 plus 6 or 18, correct? And that's 2/3, isn't it? Well, that's 4 amps, isn't it? So that's the current this way. Now, after this switch opens, the current goes to 0 as t goes to infinity, right?
Right. What I did is I found that 6 and I thought that was the answer. And so when I looked at the solution, I was confused why they
Yeah,
did.
but you know, you're doing the solution always starts with the current through the inductor and then using that to get whatever you want. First, you got to get that current. The current through the inductor is 4 amps for t less than 0, isn't it? That's
Yeah.
all right. So it's 4 amps, right? And now once you know it's 4 amps right here, and you see what I'm doing, don't you?
Well, I'm still confused because why do you multiply it by the 12/18?
Do you remember how current division works?
Yes.
Well, I said I have 6 amps flowing this way, right?
Right.
All right. Where does it split between? It splits between that 6 ohm here and this 12 ohm that's in parallel with it, which is 4 and 8, right? So I'm going to put it there. So I've got a total of 6 here, and I've got 12 here, right? But here's where my inductor is. That's what I want. I want this current, don't I? So how do I get that current? I take the total current into the parallel combination. Then I multiply it by the opposite resistance, 12, over the sum. 6 plus 12, right? And that's 8. Sorry. Are you with me?
Yeah.
That's simply what? That's 12 over 18, or 2/3 of 6 is 4 amps, isn't it?
Yeah.
So that's the current through here for t less than 0, right? Did you see that or not, Amanda?
Yes.
If that's 4 amps is the current, this is the thing you need. Then you take a look at this, and when that switch opens, do you see the current through that inductor is 0 as t goes to infinity?
Yeah, I got the rest of it right. That was just the one part I was
But,
wrong.
I mean, do you understand what I'm doing though?
Yeah.
That's the key. And then once you have that current, all right, I mean, then you have to get R Thevenin, which is going to be R Thevenin is what? It's 12 and 6 or 18, right? Just sum up all those resistors, you get 18. So then I get L 2 over 18, or 1/9 is tau. And then I get K1 e to the minus t over tau plus K2, but the current goes to 0, so forget K2. So it's just what? It's 4 amps e to the minus t over tau is this current, but they want this current. That's going in the opposite direction, so it's minus the current we calculate. Okay?
And so if we're like looking for one that's in parallel with the inductor, is it always going to be like negative?
No, wait a second. You say you're looking for one in parallel with the inductor. Here, they're all in series with the inductor, aren't they?
Well, by the end, but like if you look at the whole circuit, like again.
You're talking about t less than 0?
No, I'm talking about the current from like the one they're like actually looking for, the current of t greater than 0 of that like 8 ohm resistor.
Yeah, but you need this current to get that current.
Right.
And so that current here, because for t greater than 0, that part of the circuit's gone. That current is just minus this current, isn't it? This goes this way, this current goes this way, isn't it?
Okay.
You follow me? And I will give you a piece of advice with these problems. You want to make sure that when you're going through them, that these look, once you go through them the first time, you can do them without any solutions. You can do any of them fairly quickly just by inspecting. You know the steps you're going to take. It should be like that obvious. Then you've got it. If you're struggling with this one, oh, I don't know how to start, don't know what to do, then you need to really revisit this, because these kind of problems are simple 3-step problems. T less than 0, t goes to infinity, match boundary conditions / find R Thevenin, and then you're off to the races. Anything else just becomes finding K1. These are not difficult by any by any stretch of the imagination, but they require you to get familiar with them. I promise you, if you've got to spend time. I once heard somebody, I think I forgot if this is at a German professor named Feuchtwang. I don't know if it's him that says, because you need to, it's basically you got to develop fingerspritzen. It means you have to have a absolute feel for this. You take one look, you know what to do and why to do it. It's not something you're struggling with. It should be that obvious with this level of problem. Okay, and it takes time. Some people get it in an instant, and some people it takes time. Other questions? Hey, if you got some more, can you give me 1 second? Just 1 second. I have a dog out here that's not feeling too well.
Joseph, the other time that you recorded, did you have to combine them before? Because like whenever I record, a lot of times the audio and the video will be separate. I have to combine them. Did you have to combine yours?
No, I just took the video file and uploaded it, and I checked it, and it seems the video file included the audio.
I don't know what's wrong, or maybe I just don't have enough backspace.
It seems to me like the video will always include the audio, but it has a separate, I think, .wav file that is just the
where you
audio.
have different. Okay, I'll check that way. Today I put it to record on cloud. I don't know how I'm gonna reach that, but hopefully it will appear somewhere. This is the first time I'm trying the cloud thing because I don't have much space on my computer.
Okay.
The other time, did you record directly to your computer or you did cloud?
I recorded directly to my computer. I also bought a second hard drive too, just for this semester.
Okay. I'll check and see. Thank you.
No
but
problem.
yeah, next time just offer we can both be co-hosts just in case.
Yeah.
I don't want to be the one like losing it and not having, just to make sure that we both have it.
Yeah, I missed last class because I had extra time and I have a test class just before this. I had a test that took double time.
What's your major?
Materials.
Oh, cool.
Okay. If you have questions.
I do have a question.
Hey, I want to ask you something. Hold on. Can you see this yourself or not?
What is this that you're referring to?
The paper?
No, not the paper. I put I can see you and I can see Amanda. No, I can't see Amanda. I can't see Jessica either, but I can see you. But you can't see what yourself, in other words. All right.
I can see myself.
Oh.
But like through the regular, what is the UI?
Yeah. I got you on that one. All right. Anyway, more questions. Jessica, you're still there, and so is Amanda, and so is Joseph. All right. What question?
Earlier in the class, you were talking about where is it? I think it was. Anyway, it was the problem where you had the you asked in a very confident tone this 6 plus 6 plus 3, and that's in series, and you can all tell this. Are you sure about that? Can you all tell us? Well, I couldn't tell.
This?
Yeah. I didn't understand why that was in series.
All right. When this is gone, right? For t greater than 0.
Yeah, I will say when I was learning this, I had to like redraw it to be able to see it in series first, if that helps you, Joseph.
I'll tell you what. Maybe this is. I hate to say it. My assumption is that everybody worked through these problems and like scratch their heads so they can see this. If you haven't, I'll do this one because now I'm not under time pressure. This Zoom stuff is a different kind of problem for me, trying to manage time because I'm used to technology being seamless, never having a problem. That's not the case. You can leave your video on if you don't mind, but if you don't want to, you don't have to. So I'm going to redraw it, but I'm going to combine the 4 and the 8. This is problem 3.43. So I'm going to have 12 ohms here. And then I've got a current source of 120 milliamps here. And then, do you want me to go for T? I'll go for T less than 0 because this is, we'll start there right at the beginning. There's the switch and it's closed. Then I had 3 ohms. Hey, Amanda, make sure you pay attention to this part too. That's a short. And then I had 6 and 6 or 12 ohms. Now, the reason I'm combining them now is because for T less than 0, it's not important to separate them. Y'all see this?
Yeah.
What I want is this current, right? That's the current I'm after right here. All right, now, if you look at this, Amanda, y'all agree with, do you agree with my redraw, Joseph and Amanda?
Yeah.
And Jessica, if you're still there?
Yes, sir, I'm here.
Now, if that's the redraw and you agree with it, you see how this 12 and this 12 are in parallel,
Yes.
okay? Amanda?
Yes.
I'm going to combine them and make them 6, but I'll redraw it. So I have 6 ohms here. Then I've got the 120 milliamp, right? Right here. Then I have the 3 ohm, and I'm after this current I, right? Are you with me?
Yeah.
Yes.
Amanda, you too?
Yeah.
Now, what is this going to be? Well, you see how we have a node here? This is all, these are all in parallel. I got 120 milliamps in there, right?
Yes.
Mm-hmm.
Some of it's going to go this way, some of it this way. The way I find out how much goes through the 3 is I take the total current, 120 milliamps, and I multiply it by the opposite resistance over the sum of the 2, or 9.
Mm-hmm.
That's current division. Amanda, do you follow me on that?
Yes.
And that would be 80, wouldn't it? So IL for T less than or equal to 0 would be 80 milliamps. It's 2/3. So 3 into 120 is 40 times 2 would be 80 milliamps. Got me?
Yeah.
Mm-hmm.
Now for T greater than 0, right here, T greater than 0, this switch flips, right?
Yeah.
And it takes that out. Do you agree with that?
Yeah.
Amanda?
Yeah.
I'm going to just redraw that part without all the blue paint. So for that, I have this. And that's the direction for IL of T, right? And they actually want this. Do you agree with that?
Yeah.
Mm-hmm.
You can leave your mic unmuted, Jessica. There's just 3 people here. It's not going to be a problem. Everybody agree with this. Now, look, by inspection, without any deep thinking, what is IL as T goes to infinity, and the reason?
0, because there's no source.
Yes, and always remember that. If there is no source to sustain a current or maintain a voltage, it is necessarily 0. Okay, we got that. Now, what is R Thevenin? So here's the thing you were asking about, both of you. You can literally imagine cutting that inductor, ripping it out of the circuit, and now measuring the resistance between these two X's. Do you follow me? Mentally, just tear that out. It's gone. What would that resistance be?
0.
Careful. It's gone, not shorted. Gone. Ripped out.
Wait.
Aren't they all in series? Literally take that out of there. And then, you know, if you snip that out, rip it. So it's an open circuit right there. No current can flow.
Oh, so it's 3 plus 6 plus 6?
Yeah, or
I thought you went from negative to positive. So you'd only,
resistance, not voltage. Resistance, not voltage, right? Effectively, don't we just have a resistance of 3? And then, well, I put it up here, 3 and then 6 and then 6, right? And then you're back. And here's where the inductor was, right? I just straighten that. Rip it out with your mind. What's between here and here? Isn't that 3 plus 6 plus 6 or 15 ohms?
yes. Okay. I was
Amanda?
thinking of the voltage across the resistor.
There's no voltage. We're resistance. Resistance.
No,
Resistance.
yeah,
Not
no,
voltage.
yeah. There's no R. I was thinking of R Thevenin across the resistor.
No.
V of T. But I understand now that I was looking at the wrong thing. And
R Thevenin is always across the element, either capacitor or inductor, that you want the actual behavior. You want to define the behavior. So this is 15 ohms, right?
yes.
Amanda, can you see that? You sound distant. All right, what's tau? Do you want to tell me, Amanda? Maybe you don't.
It would be L over R.
Yeah, if you're getting lunch, I don't blame you. We're going to get some when I'm done with this.
So it would be the 0.6 over 15.
Right, exactly. Now, are we okay with that?
Yeah.
Now we have an equation. We have IL of t equal simply 0. Is it 0.6, did you say? Or no, it's 80, right? 80 milliamps times 10 to the minus third. That's milli is 10 to the minus third times e to the minus t over tau. And I don't care what tau is, but you know what tau is, right? It's L over R Thevenin, whatever that comes out to. It's fine with me. All right, now if I have that, now listen. Do y'all see that that current is circulating this way, right? It's going this way, right?
Yes.
Yeah.
That means it would give rise to a voltage plus to minus here, and I'm just going to call it V prime of t equal to, and I'll put it right here, V prime of t would be equal to 6 times this. If you want to write it down, you can, times 80 times 10 to the minus third, e to the minus t over tau. That would be the voltage plus to minus, right? Joseph?
I started writing stuff down and you lost me.
Well, I'm getting at this. It's a basic concept that we started with early on. Plus to minus V here.
Yeah.
If you have a current I of t here, and that's R, right? V of t is equal to R times I of t. That's the fundamental definition of the polarities and when current goes into the positive terminal such that it defines the voltage V of t equal R, which is strict positive, times I of t.
Yes.
Agreed?
Yep.
All right, here, you'll notice I have the current going this way, counterclockwise. So positive current enters this resistor, which is 6, giving rise to a plus to minus voltage of 6 times 80 times 10 to the minus third, e to the minus t over tau. That's the voltage here that I'm calling prime. Amanda, can you see it?
Mm-hmm.
And you realize that this voltage is just minus that, because think of it as the leads of a meter. The minus is where the plus is where the minus is. It'll just be minus that, okay?
All right.
Good, Amanda?
Yep.
You understand why they're in series?
Yeah, when I was first doing these, I had to like redraw it to be able to see they were in series. But
That's fine.
now I can like see it normally, but yeah.
Today's been a kind of a strange day for me. I have a sick dog. Well, a dog that's not well. I don't know how sick she is. And then this stuff with the doc cam because of malware bites and all sorts of little things. Just one of them days.
Yeah.
I hope you got something out of the lecture. Now, when we cover power, I want to tell you that you got to be real attentive because power can confuse you, but I'm going to try to make it as simple as possible and work a lot of problems. That's where you see how the applications are. Have you all you've had power, the concept of power, right? Power in electrical, for electrical components is really voltage times current, but power in general is the rate of doing work, the most fundamental thing. Your book will have a very fundamental discussion, but it'll assume a whole lot, and that's why I'm going to back it up a bit. That's the reason I used a simple resistor and an AC source to try to show you what average